Inside any financial instrument that uses leverage to amplify returns, there is a hidden mechanism generating intense friction. Left unchecked, this friction will slowly grind the portfolio down to zero from the inside out. To see exactly how this mathematical decay works, we can compare two heavily traded assets. First, the standard NASDAQ 100 ETF, ticker QQQ, which offers 1-to-1 exposure to the index. Second, its leveraged counterpart, TQQQ, which promises 3 times the daily return of that same index. This split-screen chart tracks a perfectly sideways market over a 2-day period. On day 1, the underlying index goes up exactly 10%. On day 2, it drops exactly 10%, returning precisely to its original price level. The 3x fund matches this perfectly, rising 30%, then falling 30%. But when we multiply these percentages together to calculate the final balance, a massive discrepancy emerges. The 1x investor loses a marginal 1%. The 3 times investor loses 9%. The underlying index returned to the mean. The leveraged fund tracked the daily multiples flawlessly. Yet the total loss on the leveraged side is exactly 9 times larger than the unleveraged side. Retail investors often assume this heavy value destruction is the result of exorbitant management fees, bad execution, or poor index tracking. The actual cause is volatility drag. It acts as an inescapable tax on geometric compounding. This drag operates as a literal law of financial physics. It aggressively punishes any portfolio attempting to maintain constant, linear leverage across multiple trading sessions. To understand how to survive trading these instruments, we must derive the formula, expose the mechanical trap, and engineer a mathematical workaround. Treating market returns as simple addition is a fatal error. Long-term wealth is dictated entirely by geometric compounding. On the left of this mathematical canvas is the arithmetic mean, the simple average of individual daily returns. Leveraged ETFs optimize for this. On the right is the geometric mean, calculating multi-period compounding. This represents the total cash you actually possess. Fund managers are paid to hit the daily arithmetic target on the left. Your personal net worth is determined entirely by the geometric reality on the right. To bridge these two equations, we have to apply the natural logarithm. This mathematical operation converts compounded multiplication into manageable addition. By calculating the difference between these two formulas, we can map the exact financial penalty an investor pays when translating daily arithmetic promises into long-term geometric realities. To estimate the behavior of logarithmic functions near zero, mathematicians use the Taylor series expansion. If we substitute our daily percentage return into the variable, we can simplify the math. Daily market returns are small enough fractions that anything raised to the third power or higher approaches zero. We can truncate the equation. That negative squared term remaining is the mathematical source of friction. When we calculate the expected value of these returns across hundreds of trading days, statistical variance, which is the asset's overall volatility, maps directly into this squared term. Substituting our initial variables back in gives us the definitive formula for multi-period investing. Actual geometric return equals the arithmetic average minus exactly half the variance. Volatility mathematically taxes compounding. Now we apply leverage. We insert a constant leverage ratio, L, directly into the volatility drag equation. Multiplying your capital exposure by a leverage ratio inherently multiplies your exposure to the underlying asset's volatility by that exact same ratio. Because the volatility term sits inside a squared mathematical function, the leverage ratio is also squared. When an investor buys TQQQ, they assume a constant leverage ratio of 3. 3 squared is 9. Because volatility acts as a quadratic penalty in the geometry of compounding, tripling your leverage generates exactly 9 times the physical drag on your portfolio. Abstract calculus explains the presence of the drag, but the loss happens physically through the fund manager's daily accounting requirements. This ledger shows the starting balance sheet of a 3 times leveraged fund. An investor puts in $100 of equity. The fund borrows $200 of debt, yielding $300 of total market exposure. The leverage ratio is perfectly balanced at 3. If the market increases by 10%, the total exposure grows to $330. The fixed debt stays at $200, leaving $130 in equity. The math here creates a severe structural problem. $330 of exposure divided by $130 of equity means the leverage ratio organically dropped to 2.54. The fund is violating its 3x mandate. To restore the balance, the manager is forced to borrow more money and buy more shares at the highest price of the day. When the market drops, the math runs in reverse. The leverage ratio spikes, forcing the manager to liquidate assets at the absolute bottom of the drop just to pay down debt. The mandate to maintain a constant leverage ratio creates an automated doom loop. The fund is legally required to buy high and sell low every single day. This forced trading is the real-world manifestation of the volatility drag. If constant rebalancing guarantees mathematical decay, capturing multi-period leverage requires a structure that can dodge the squared penalty entirely. This chart models a severe, continuous market crash. First, linear debt, like a margin loan or a rebalancing ETF. As equity shrinks against fixed debt, the leverage ratio accelerates violently. The red line arcs straight toward a fatal margin call. The alternative requires nonlinear instruments, specifically deep in-the-money Leaps calls. Because the Leaps call is a derivative contract, its mathematical exposure drops organically as the underlying asset price falls. The green line smoothly curves downward, decoupling from the exponential threat of linear debt. Options traders call this self-dampening property positive gamma. Gamma acts as a mathematical circuit breaker. It prevents the leverage ratio from approaching infinity, allowing the position to survive without triggering forced liquidation. A Leaps option is a static contract. It bypasses the daily rebalancing mandate, completely short-circuiting the buy-high, sell-low doom loop of the ETF. We can visualize this by returning to our foundational equation. For the in-the-money option holder, the geometric variance penalty ceases to apply, but leverage must be paid for. The squared variance term is replaced by theta, the fixed decay of the option's time value. Advanced investors abandon the unpredictable, quadratic punishment of volatility drag, trading it for the defined, finite cost of an option premium. Leverage cannot be engineered out of thin air. The market will always extract a toll for amplified returns. The professional edge comes by choosing to pay for leverage in the fixed currency of time, rather than the chaotic, compounding currency of volatility.